Morning, everyone. Today we're going to talk about controllability. I don't know how many of you are from control background, so and we'll connect it to networks and a bit of a graph theory. So it's going to be a mix of a couple of things, and also obviously signal processing because I come from signal processing background. Let's get started. Networks are all around us. We live in a world which is surrounded by invisible webs around us. There are several controllable network systems which keeps our society functioning. And some of them are social networks, biological networks, chemical, energy, food, and our human body itself is a huge network of different subsystems which work in harmony. So this thing came back. So the networks are everywhere. And networks are mostly, most networks are controllable. For example, think of a power grid network and we have switches, we can switch it on, off, we can control voltages, controls. So there are a lot of controllable options there. Biological networks, we control them using drugs. Sometimes social networks, we interact with people and some people are manipulating. So in that way, they control the networks. So the social networks and control are very much related. So here is an example of a control network, which can be represented using graphs. So when I talk about networks, I'm thinking about a network which carries some data, which changes over time. So think about a Dutch electricity grid network, which consists of multiple subsystems, which are interconnected and they interact with each other. And we can represent it using a graph. So here, every node would represent a subsystem in the electricity grid, and how they interact will be captured by the nodes. So by the edges. So if two nodes are interacting, we'll have an edge connecting them, and if not, there won't be any edge. So this is how we abstract a network using a graph. And what is control theory about? Control theory is about analyzing and influencing the system behavior. So if we have a network or a system, how does system behave over time? And how can we influence the system? What changes can we introduce to the system so that we can achieve a desired behavior? So this is what control theory is about. We normally represent system evolution or how the data changes over the networks using a linear dynamical system. It's one of the simplest systems which can capture our data, how data changes over time. And we particularly stick to the state space model, which consists of two equations, a state evolution equation and observations. So state evolution will tell how the state of the system changes over time. And here K represents the time index. So think about a network where xk corresponds to the signal that you observe at every node of the network. So the number of nodes will be equal to the dimension of xk. And as time change, with time, the node values will change. It can change due to two reasons. One is because of the interactions among the nodes. So one node can interact with another, and it can change the another node, and that particular interaction is captured by the first term here, a times xk minus 1. And the second term, b times uk, is the application of external controls. So this is something like applying drug to your body. So that will change the innate behavior of the system. So there are two components to state evolution. The first one is an innate behavior, which is a times xk minus 1. And the second one is external control, which is b times uk. This can be easily captured using a graph. So think about xk as a vector, where one entry of xk represents one node in the graph, which are represented by the blue dots here. And xk depends on xk minus 1, that the state of the system at the previous time, because the state is changing over time, and how that dependence is captured using this matrix A. So here you can see that if the state of node, let's say 832 is non-zero, which means that the state of node 2 will influence the state of node 3 at time t. So that's why you have a connection which connects x2 and x3. And then there are some external inputs that we apply to the system. The external inputs need not affect all the nodes. So in this particular example, there's an external node, there's U2 and U1, and they would not, U2 will influence X5 and U1 will influence X2. So, and that's captured by this matrix B. So this is how a linear dynamical system can be captured using a graph. To repeat, there are two aspects here. The first one is a matrix, which captures how the nodes are connected to each other. And there's a B matrix, which connects how the external inputs would influence each node. So these are the two important characteristics that we can capture using a graphical representation of a network. Or these two representations are the same. And then there are some observations. Observations are how we measure the network. We may not be able to measure all the quantities individually. We may not be able to measure xk exactly. So in most cases, we see a projection of xk. And so that's what we represent using observations yk, which is equal to c times xk plus some noise. The C matrix will capture how we collect the measurements. Right. So to understand this, let's look at an example. So think of a social network. A social network is basically a collection of people. So here, a node represents a person in the network. And what could be a state? A state could be a social opinion. For example, all of us have some opinion about the social safety, or duty to your death, or something other, or a movie rating could be an example of a state. So everybody will have their own opinion. This can be thought of some sort of a rating that people have about a particular entity. It could be movie rating, it could be political inclination. So that would represent a state. So every person has an opinion, and that represents the collection of all the opinions will represent the state vector. And then there is a transition matrix, which is the A matrix, which will tell how these people would influence each other. People will talk to each other, and then they get new perceptions, new insights, and they change their opinion over time. And that is what is captured by this A matrix, which represents social connections. It could be social connections could represent people living in an area, people working for a company, or a social media group where people discuss about things. It could represent different things in different contexts. So this A matrix represents these connections, how the different nodes are connected to each other. And then there are some external inputs. External inputs could be social influencers, people who want to influence opinions deliberately. This could be a marketing agent who would come and talk to you about a particular product and say good things about the product, or somebody who would give you a free sample of a product for you to test it out and see if you like it or not. So these are some external inputs. These are not unbiased opinions, but these are people who try to bias people. So that could be an example of a social influencer. This could be even political leaders or people who have good reputation. So think about the head of NASA coming to us and say that, oh, well, new studies show that fried chicken is good for heart. Okay, I mean, you might say, oh, not really, but why do you think so? You might be a bit biased, right? You want to know more about it. You want to discuss that. But imagine a kindergarten child coming to you and say, fried chicken is good for your heart. How do you react? Like, okay, child, you'll know about these things later on. So some people have more reputation, and then these people can influence you more. So this kind of a reputation is, and if they want to manipulate you, they can use this reputation to manipulate you. So that is what is represented by social influencers. These could be paid influencers as well. And what are observations? Observations could be a movie rating that you see on IMDb, or some sort of surveys where we collect opinion about some products from certain people. So observations doesn't represent the entire network's opinion, but a part of it. For example, a movie rating would show how collectively people think about a particular movie. A survey will tell about what some part of the society thinks about a particular product, and so on and so forth. And this is an example of how a social network, which can be represented using a linear dynamical system, and also it can be represented using a graph. And what is sparse control? Sparse control is minimum intervention. So what does that even mean? So think about a huge network, and we want to do some control over the network. And in most cases, it's not possible to influence each and every entity in the network. And because of that, in most cases, people resort to sparse control, where you can only influence few entities in the network. So let's look at some examples. So think about a biological system and you want to use a minimal drug control because you don't want to disturb the system. We want to make minimal changes to the system and still want to achieve a particular behavior. So this could be one case where we want to use sparse control. Another example could be a resource constraint system. So think about a bunch of drones moving around, and there's a controller which talks to the drones over a band limited channel, and then it doesn't want to send out very dense controls to all drones, but it want to use a sparse control so that it has low communication and computational burden. So sometimes because of computational resources, we have to use sparse control. Another example is social network. If there's a marketing agent who wants to give free samples, he cannot go and give it to all the people in the network, but maybe try few people. Or if you want to have a word of mouth kind of an advertising, we can try to influence some celebrities and then ask them to influence people. So, so highly reputed people can have more influence. So we can try to identify such people and then try to make a difference using by influencing fewer people. And the system will eventually get controlled because of the word of the mouth effect. Another example which you cannot see, but it's there. So another example is cyber physical attacks. So if you want to attack a system, then you don't have access to all the nodes in the system. And cyber physical attacker would want to access only few nodes, but yet make a huge difference. For example, think of a power grid. You want to switch off certain things here and there, and then it has a cumulative effect and it can affect the whole system. So there are different reasons, and mostly because of resource constraints, people try to use sparse control to control a system.
Oh, now it should work.
Yeah. And what is sparsity? So sparsity is basically represent a vector. It's a control vector with lots of zeros. And so think about a system with a lot of actuator possibilities. For example, the social network case, a lot of people, and you want to pick and choose few people who can influence the entire network. So in that case, the people that you would choose will have a non-zero control and the others will have a zero control. So for example, a kindergarten child will have a zero control because he has lesser influence in the society than compared to somebody like, I don't know, dean of electrical engineering, who will have a better say in certain things. So, so this is what we mean by sparse control. So basically, if you look at the control vector, it's a big long vector with mostly zero entries, which means most of the nodes are uninfluenced and only very few will have non-zero entries. And that's the one good thing about sparse control itself, it admits compact representation. What I meant is, if you want to represent a big long vector, you don't need to store all of them. Since most of them are zero, you can store it very efficiently. So that saves, for example, low communication. It will lead to low communication costs when you try to transmit over a band limited signal. And what does this talk about? This talk is about sparse control in discrete time linear dynamical systems. When we ask the following questions. So the first question is, we have a system and we have a lot of actuators. We have a lot of possibilities to control the system, but we use a few possibilities out of the options. So does it actually work? Is it possible to get any desired behavior, or is it possible to control the system by only using few nodes? That's the first question that we want to address. Second question is, yes, if the system is controllable, then how can we design such a control system? For example, in case of drug control, like which parts should be changed to make sure that the whole biological network attained a particular behavior. Or if you try to detect a cyber physical attack, like how do you estimate this sparse control? Somebody has attacked you and you know that it's sparse control because they don't have access to the entire network. And how do you detect a sparse control? So these are the second part of the system. And we also look at a small case study where you look at social network manipulation using sparse control. So this is how we have organized the talk for today. Any questions so far? All right. Okay, let's revisit our math equations. We work with state space model. Where we look at equations state evolution, which is described by xk is equal to a times xk minus 1 plus b times uk. And we are looking at sparse control, which means that we assume uk, which is the sparse, which is a control input, is sparse, which means the L0 norm of uk is much less than the size of uk itself. We can think about two types of sparse control. One is time invariant and the other one is time varying support. What I meant is in time invariant case, people can choose different non-zero values across time. So at first time, we can try to pick 3 people here and make sure that everyone else is 0. And the next time we can try to influence 3 nodes and make sure everything else is 0. So you can basically you choose fewer people, but over time you choose different sets of nodes or people. That is what we meant by time invariant case. And then there is a time, so that is a time varying case. And there's a time invariant case where we just pick a few among all the available options and then always try to use a non-zero control only using those nodes. So these are the two different cases that we're going to discuss today. All right, so let's start with the formal definition of controllability from the control theory literature. So given a system, a linear dynamical system, it is said to be controllable if using a set of admissible control, we can start from any initial state x0, and achieve any final desired state. If there exists such control inputs, then we call that system as controllable. So to give mathematically, let's say you start from x init. So this is the initial state from which we are starting, and we want to move to x final, which is a given final desired state. For example, in case of a marketing agent, maybe before the product is not launched, nobody knows about the product, and you can think about the state of social opinion as like a 0 vector, and then your goal is to the X final is to drive to make sure that everybody buys it or everybody's good opinion about it. So you can have a desired final state. And if you use the linear dynamical equations and write it out, you can see that the X final and X initial are related with the control inputs using this matrix, which is called the controllability matrix. So controllability matrix, if you look at the controllability matrix, it has different powers of A. So you have terms like A power K minus 1, B, A power K minus 2, B, all the way to B, where B is the input matrix and A is the transition matrix. All right, and then there's a big long vector, which consists of all the control inputs that we apply over time. So U1 is the control input at time 1, U2 is the control input at time 2, all the way up to time k. And each of the UIs are vectors themselves. All right, so how do you ensure that the system is controllable? If you want to make sure that you reach that exists a solution to this system of equations for any x final and x initial, then it's clear that the rank of this matrix should be full. So the simple controllability test is rank of this controllability matrix should be equal to n, where n is a number of rows in the controllability matrix. This particular test is called the Kalman test and controllability. There's an equivalent test called PDH test, which is mathematically identical to Kalman test, and it has a very simpler form. What it says is rank of this matrix, rank of A minus lambda I accumulated with B should be equal to n, where lambda can be any complex scalar. So it's clear that if lambda is not an eigenvalue of A, then this is going to be a full rank matrix and this is satisfied. So in effect, we have to check this condition only for all eigenvalues of A. So for every eigenvalue of A, lambda, if this matrix satisfies this condition, then that will ensure that the system is controllable. So these two are equivalent conditions for controllability. However, this is a classical notion of controllability. That means we are not imposing any sparsity constraints yet. And now what we are trying to do is, if we impose sparsity constraints, which means each of these UIs are sparse, then how does the controllability condition change? All right. So we assume that, so we'll first look at the time invariant case, which means all the UIs will have the same support. The non-zero entries will have the same indices over all the UIs. So what will happen in that case? So let's assume that the support of UI, which means the indices of non-zero entries of UKs, is fixed. So that's a set S. So it is a subset of all possible options. So you have n entries in U case, and we just choose a small subset of that, and we only activate those subsets every time. So what happens is you can replace this U1, U2, all the way up to UK with only the non-zero entries, because all other entries are zeros, and when you multiply with this matrix, it has no effect. So we can just replace U case with UK, just restricted to the support S. And therefore, we have a new controllability matrix. So if you look at these controllability matrix, most of the columns are multiplied with zeros, so we can throw them out. And the resulting controllability matrix will have this form. So everywhere, instead of B, we replace with B restricted to S, where S is a set of columns of B which are chosen. So this is a new controllability matrix. And how do you test if this controllability matrix, if this system is controllable? So this is a classical system because UKs are now all non-zero entries, and we have to just check the rank of this matrix. So with sparsity constraint and time invariant support, the system is controllable if and only if this particular matrix is controllable. And that gives us a very simple equivalent PPH test as well. So if you look at this controllability matrix, this is the controllability matrix of a new system with transition matrix A and input matrix B sub S. So we can just use a classical controllability theorem and we can write PPH test. All we have to do is wherever we see B, we should replace B with BS. So that is the controllability test. And if you want to check whether it's possible to control the system with N S inputs, then we have to check whether there exists an S such that this condition is satisfied. So that is a straightforward extension of classical control theory. But this works only if the support is time invariant. That means we choose the same subset of actuators at every time. Now let's look at the time varying support case. So in time varying support case, each of the UKs are sparse, and then they have different supports. The supports can change over time. So let's say that the support of UK is SK, which depends on K, and we'll look at the controllability condition here. So what happens here is every time you choose a different support, and therefore the first B will get replaced with B sub S1, the second B will get replaced with B sub S2, and so on and so forth. Therefore, it doesn't have a pattern similar to what we had earlier. And then we want to make sure that there exists an S-sparse vector which would attain controllability. So this system of equations should be solvable for some S case. That's the goal that we have. And we have different options for S case. And if you look at the span of this matrix over all possible values of S case, then we get a finite unit of subspaces, which means at one time you can pick a fixed number of support, and so we can choose S1, S2 all the way up to xk minus 1. That will give you a matrix, and it will have its own column space. And then we have different options for each of these SKs. Right? If you have n entries and you choose S out of n entries, there are n choose S options to do that. So for every different options of SKs, we can construct a different controllability matrix. If your only constraint is that your UK should be sparse. So for every UK can have n choose S options for its support. Therefore, we can the column space of all possible controllability matrix with sparsity constraint will be a union of spans of different matrices. And therefore, the condition that we are looking for is that we look at the union of different subspaces, and this union should be equal to R power n, which means we'll be able to pick any vector x final and x initial, and then we should be able to find this supports at S1, S2 all the way up to Sk, which can drive your system from x init to x final. So we want to, the controllability condition reduces to checking whether R power n is equal to a finite union of subspaces. All right. But from our linear algebra class, we know that union of two subspace is another subspace if and only if one subspace is contained in another. So this is a finite union of subspaces. R power n is also a subspace. So finite union of subspaces is equal to R power n if one of these subspaces contain R power n. So therefore, the controllability condition changes as there exists S1, S2, all the way up to Xk, some Sk's, such that this particular matrix, the span of that matrix is equal to R power n. In other words, rank of A power k minus 1 BS1, A power k minus 2 BS2, all the way up to BSK is equal to n. So if there exists one such set of supports, k supports, which can satisfy this condition, and then that is a controllability test. So this can be thought of as a Kalman type controllability test, where we try to evaluate the different powers of A and check the rank condition of a matrix based on that. But there is a problem with this condition. So the problem is, it's hard to evaluate this condition. So if I have a system and I say I want to check whether that system is S-sparse controllable, then I have to run through all possible supports to make sure that this condition is satisfied. And this could be a combinatorial problem. So can we think of a simpler condition which is equivalent to this, where we don't have to do a combinatorial type of check? That's what we try to do next. So for that, we look at some necessary conditions. So think about sparse controllability. What does that mean? It says that a system is controllable using sparse inputs. If a system is controllable using sparse inputs, it should be controllable without the sparsity constraint, because controllability is a looser version compared to a sparse controllability. If you can achieve something with an extra constraint, you should be able to achieve it without constraint as well. So sparse controllability naturally implies controllability. And therefore, we know that if system is controllable, the PBH test should succeed, because that's a test check whether the system is controllable or not. All right. So we try to work on this. So let's say that a system is sparse controllable. And we see that if the system is sparse controllable, the Kalman type test in the lower box here should be satisfied. So if the Kalman type test is satisfied, there exists a K and a set of supports such that a rank of this matrix is equal to n. Look at the first few columns of this matrix. We have an A sitting on the left side of all these columns. So we can say that this part is A times some other matrix. Or in other words, the column space of the first few columns of this matrix is a subset of span of A. So if I replace the whole thing with A, the rank is not going to reduce. So what I do is, if the rank of this matrix is n, I can clearly say that rank of this first bunch of columns replaced with A should also be equal to n. And therefore, we can further bound this. If rank of A plus a bunch of columns from B is equal to n, I can clearly say that rank of A plus S, where S is the number of columns in B, is also equal to n. Because at most, BSK can have S columns, and therefore it can increase rank by S. So what I'd say is that if a system is sparse controllable, then the sparsity level S is greater or equal to n minus rank of A. This is a necessary condition. Why? Because if system is sparse controllable, this condition needs to be satisfied. System is sparse controllable, it satisfies the Kalman type test we derived. And if that is satisfied, then sparsity level should be greater or equal to n minus rank of A. So this becomes a necessary condition for sparse controllability. So a system is sparse controllable if it is controllable, as well as this rank condition is satisfied. And if it's controllable, it should satisfy the classical PPH type test. So the necessary conditions for sparse controllability are two. The first one is it should be controllable, which means it should satisfy the classical PBH test. And the second one, the sparsity level should exceed a given threshold, which is n minus rank of A. So if one of these conditions is violated, the system is not sparse controllable, and therefore these are necessary conditions. For example, the first condition is violated, then the system is not controllable, which clearly means that the system is not sparse controllable. The second condition is violated, all these bunch of equations will be violated, and therefore the system is not sparse controllable. So these are some simple necessary conditions for sparse controllability. What is beautiful about these conditions is that these are easy to check. Look at the first condition. we have to only check this condition for all eigenvalues of A, which can be done in polynomial time. The second one is a simple comparison. We have to just evaluate the rank of A matrix and check whether sparsity level exceeds that particular level. So unlike the previous test that we derived, it doesn't need a combinatorial check to check whether the system is sparse controllable. However, this condition is only necessary. It's not sufficient, but we can prove that this is also sufficient. I'm not explaining the proof here, but we can show that these conditions are also sufficient for a sparse controllability, which could be a bit surprising, but is a very easy proof. So to summarize, what we show is that if a system is sparse controllable, there's an if and only if condition that it needs to satisfy two conditions. The first condition is the controllability itself, which is pretty clear. So the system should be controllable and the sparsity level should exceed a particular level, which is the nullity of matrix A. And this is similar to the classical PBH test. And it is easy to verify. There is no combinatorial check. And yeah, so any system which is controllable is also sparse controllable as long as sparsity exceeds a particular level. That's the takeaway from the discussion that we had so far, which is a beautiful result because it tells us what is the minimum number of people that I should influence to make sure that I achieve a desired behavior. Or it gives some insights to how do I design my sparse control if I want to achieve something. If you go below this level of S less than n minus rank of A, then the system can be uncontrollable. This leads to a couple of other interesting results, which I'll skip for today. For example, this can give something called Kalman decomposition type procedure, which can separate our system. Suppose that the system which is not sparse controllable, then we can separate the space into three different parts. So one part which could be controllable. So let's say our S is less than n minus rank of A, which means that the system is not controllable. And then we can clearly identify which part of the system is controllable, which part is not controllable, which part is not sparse controllable. So we can divide the whole state space into three different parts. I'll not go into the details, but this is one result. And we can also derive the number of inputs that we need to guarantee controllability. So if you know that a system is sparse controllable, then the next question is, and we know what is the minimum sparsity level that we need. The next question is, how do we design the controller? How many number of control inputs do you need? So that you can start from one initial state to arrive at another initial state, which is equivalent to this capital K in this equation. So how many number of control inputs should we apply? And there's a bound for that as well. And interestingly, this is upper bounded by capital N, which is a state dimension of the state space. So if you're trying to control a system with n nodes, then we need to apply n at max n sparse inputs to make sure that the system arrives at a desired behavior. That's the takeaway of the system. And this also matches the non-sparse case. So if we have a non-sparse system, so you can apply any number of control inputs, then n is the upper bound in that case as well. In the classical non-sparse case also, the bound is n. If you have sparsity constraint, even then you need at most n number of control inputs to ensure that system starts from a given initial state and arrives at another state. All right. And we have derived a bunch of extensions for this result. So this is what we saw first. If we have sparse controllability with fixed support, then we need a combinatorial check to ensure that the system is controllable. But if we have sparse controllability with time-varying support, then the controllability test simplifies. We need to check two conditions, controllability and a limit on the sparsity level. This could be extended in multiple ways. The one is non-negative sparse control, which means think of a system where you can only apply positive inputs. So UKs are not only sparse, but they only have positive and non-negative entries. So in that case, this corresponds to a system like a radiator. So if you have a bunch of a radiator which tries to control the temperature of a room, you can only give heat. You cannot take away the heat, right? So in that case, the control is always positive. It's not negative. So for such systems, if you also impose sparsity constraint, you can show that non-negative sparsity, non-negative sparse controllability is same as non-negative controllability plus the same bound on sparse control. So that is another result. then we can think of output sparse control. So at times we don't want to make sure that the entire system is controllable, but we want to make sure that a part of the system is controllable. Think of an election campaign where the goal is not to get all the votes, but to get the majority of votes. So there you don't want to control the entire system, but a part of the system. So in that case, if you have sparsity constraint on the control, then output sparse controllability is equivalent to output controllability and some other bounds on sparsity. Then this bound will not work. And then as a notion of stabilizability, stabilizability refers to a system where you apply bounded inputs and then you can drive the system to zero state. So that is called a stabilizability. And if we can only apply sparse inputs, then sparse stabilizability is equivalent to stabilizability, where there is no bound on the sparsity. As long as sparsity is greater or equal to 1, sparse stabilizability and stabilizability are one and the same. So these are some extensions of controllability results that we have with sparsity constraint. Right? How much more time do I have?
5 minutes.
5 minutes, okay. All right, then I'll skip these things. Maybe a few words about design and estimation of control inputs. So we have derived some conditions under which a linear dynamical system can be controlled using sparse inputs. And the next question is, how do we design such control inputs, or how do we estimate such control inputs? So let's quickly look at the design problem. So the design problem is, given an initial and final state, how do you choose a sparse control inputs? We recall that we need at most n sparse inputs to start from any initial state to any final state, as long as the system is controllable. And therefore, we can write this as a system of linear equations, where the only unknown is the set of sparse inputs that we applied. So we can just solve it using any least square approach if there is no sparsity constraint on U. But if we want to enforce a sparsity constraint of the control inputs, then we can have to use other techniques. One naive approach is to use the standard compress sensing or sparse recovery algorithms. But the problem is it doesn't ensure that each of the UKs are sparse. In general, if you use a sparse recovery algorithm, it will make sure that the entire vector U, which consists of all the inputs, is sparse, but it doesn't ensure the individual sparsity on each of the control inputs. Then we have to resort to more specialized algorithms. So there is a notion called piecewise sparsity. What it does is it takes a big long vector U, divide into small chunks, and ensure that every piece is sparse, which is what we want. If you look at this big long vector U, we want each of the UKs to be sparse. It should have at most S entries. So this leads to a special structure called the piecewise sparsity. And there are some algorithms which can do this. And if you look at the sparse control inputs with a common support, so if you assume that each of the U1, U2, all the way to UN have the same support, and then we have can use another type of sparsity algorithm. So think about this UK. So this is U1, this block is U2, and this block is U3. And the indices of the non-zero entries are the same. So the first entry of U1 is non-zero, then first entry of U2 is also non-zero, first entry of U3 is also non-zero. So what we can do is we can rearrange these entries. So if we collect all the first entries of all the vectors, we get a block of non-zero entries. If we collect the second entries of all these control inputs, we get a block of non-zero entries, zero entries, and so on and so forth. And this particular structure is called block sparsity, where there's a big long vector, it is sparse, but the non-zero entries sit together, they are clustered together. And this particular structure is block sparsity, and you can use these kind of algorithms from compress sensing literature to solve these kind of problems. Similar approach can be used for sparse input estimation problems as well, but we'll skip it. So these are the two types of sparsity patterns we discussed. The first one is block sparse structure, where there's a big long vector and the non-zero entries would sit together. They are clustered together. This is useful to estimate control inputs with time invariant support. And if the support is time varying, then we have to use this particular structure called piecewise sparse signal. To wrap up, there are two types of algorithms we can design for sparse control inputs. The one is time varying support, where we have to use piecewise sparsity, and it has very limited algorithms, or only 2 or 3 algorithms in the literature which can address this problem. It's an open area. And then there is a time invariant support, and there are plenty of algorithms which can handle block sparse structure. Okay. So to summarize, we looked at a linear dynamical system. We didn't look at the observations part yet, but we skipped it for this talk. But think about we discussed a state evolution model, and we looked at how sparsity would impact controllability of networks. If you want to design the control inputs, in the non-sparse case, we can use a least square solution. But in the sparse case, we have to use specialized sparse recovery algorithms like p-sparse sparsity algorithms or block sparse algorithms. Existence condition for non-sparse case, we have the classical Kalman and PPH test, and we need at most n number of inputs to achieve controllability. Whereas if we have sparsity constraint and if it's time varying support, then we have to make sure that the controllability conditions are satisfied and the sparsity level exceeds a particular level, which is the nullity of matrix A. And we also need n number of inputs at most to achieve sparsity. Before I wrap up, I wanted to show you one more type of graph, which is it. We recently people have started looking at something called structured linear dynamical systems. So what does that mean? So in most cases in networks, we might know that two entities are connected, but it's difficult to quantify how they are connected. For example, you know that two people are friends, but you don't know how much one person can influence the other one. It's difficult to quantify such things. And for such graphs, we have something called structured graphs. So we look at the system like xk equal to a xk minus 1 plus b uk. But A and B are not normal matrices, but rather we populate them with zeros and non-zeros. So we only know the system matrices up to their patterns. So if two people are connected, we put a star, and if two people are not connected, we put a 0. And if you're not sure whether two people are connected or not, then we put a question mark there. So this is a pattern matrix. So the actual A matrix will obey this particular pattern, but we don't know what the actual A matrix is. So these type of systems are gaining attention very recently. And we can extend the notion of controllability there as well. And there it's called structural controllability. So a structural system is controllable. There are two types of controllability there. A structural system is controllable if at least one numerical realization of A and B is structurally controllable. So if you can think of an A and B, which satisfy this pattern, and then the corresponding linear dynamical system is controllable, it's called structurally controllable. And there's a notion of strongly structurally controllable. So for every pattern, there are multiple realizations, right? And if the system is controllable for all such realizations, then it's called strongly structurally controllable. And this is a new area which is gaining some attention, and this is really connected to graph theory and zero forcing numbers of graphs. There is no notion of Kalman test or PPH test in this case, but people use graph coloring based test to check whether the system is controllable or not. But we can also think about this kind of sparsity constraints on structured structured systems as well. Okay, so to wrap up, we have seen different types of sparsity constraint. There are some open problems, obviously. We considered only sparsity over actuators, which means among the all possible control inputs, we only choose a few number of control inputs at a time. But we can think of sparsity over time as well. So we don't have to apply a control input at every time, but we can think of applying control inputs for some time, switch off the system, then switch it off again after some time. So this notion is called sparsity over time. We can also think about sparsity over feedback control. And then we discussed piecewise sparse structure, and there are limited algorithms there, and that could be one open area. And we can also think about if deep learning based algorithms can help there, because the classical or the model based algorithms are not very useful in that particular case. Another one is other applications. We primarily focus on social networks here. And the last point is sparsity plus structural controllability is almost untouched. People have not started looking at that area too much. So even the whole area of structural controllability is new. So combining it with sparsity is a completely open area. Right. These are some references. And if you're interested in this topic, you can refer to a monograph, which I published in Foundations and Trends in Systems and Control. It explains these stuff but in a simpler fashion rather than it's easy to read a monograph than reading the papers. So, but there are a bunch of papers that we have worked together. And I'll wrap up this talk with by thanking all my collaborators. I have collaborators in India, in the US, and of course here at Delft as well. So I have worked with people from 3 different continents, and looking forward to working with Africans and Australians anytime soon. Yeah, thank you so much.